Hello. Hi. We'll start in 1 minute. Hello. All right. So, how are we doing? What do you guys do all day? Like, other than, having class occasionally? Are you guys play a lot of Animal Crossing? Do you guys even play that kind of game? Stare at the wall. Procrastinate? Good question. Wake up every once in a while? My goodness. Maple Story has a leveling event. Maple Story is it's a game with a very long history. When I was your age, I used to play Maple Story. That was the start of Maple Story. See how long this game has been? It's insane. Man. Alright, let's get this started, I guess. We can chat later if you want. So, talk about triangular numbers. So, triangular numbers are kind of like, special type of numbers that has this particular pattern. It's basically like this. Okay, why is it called triangular number? Because it looks like a triangle. So 1 plus 2 plus 3, right? And then if you stack them up, then you get 2 times as much, right? 2 times 1 plus 2 times 3 plus 3, right? 1 plus 2 plus 3. And you have 2 sets, you get 2 times that. So if you think about it like that, you can basically draw any set of 2 triangle numbers, kind of like this, right? I'm gonna draw this one. Four, and you align the other side on to form a rectangle. Okay. You want to match the number. Oh, sorry. Fell. I'll move it up. How about that? Oops. Why is it? This is so annoying. 1 sec. Let me. Give me 1 sec. Let me mess with this a little bit. Do you guys feel keep moving their screen when they're playing? Is that good? Slightly higher, slightly higher. Camera's vertical? Really? One sec, let me check the screen. Ew. Ew. Okay, 1 sec. Give me oh. Okay. This is going crazy. One sec. Oh, it's back. Or I think. See, but I think it's good now. Although my frame rate needs to increase, but I think it's in the right orientation now. Yeah. Okay. So now we will slowly wait. Okay, try the right side, this one, to try to make the same thing. And once you finish, I'm slowly waiting for the frame rates to pick up. It should be up anytime now. It's back to normal. Yeah, this is like how we find area of a triangle, in a sense. All right, so if you look at the dots, okay, so we had, if you look at figure 2, right, we can treat this like 3 times 4, right? 3 times 4, because this is a rectangle. But we can also treat it as 3 times 3 plus 1. Where did that 3 plus 1 come from? Well, because part of the 3 is from the white and the 1 is from the black, right? So we can just say, why is it helpful? Because you get 3 is your, they say answer with complete sentence. You can do that, okay? You can do that. This is the white ones, and this is the extra black one when you stack it, okay? All right. So, going back to looking at figure 2, figure 2 was 2 of 1 plus 2 plus 3, right? This one, there are 2 of them, 1 plus 2 plus 3, 1 plus 2 plus 3. Now, we know that 2 of them, I can make a rectangle become 3 times 3 plus 1, right? This is your width times your length. Make sense? So then, because of that, then each part of the triangle can be used to divide by 2, and you get this. Okay? Now, can you write similar equations for your answer for part A, part B, and part C? For example, your A would be 2 times 1 plus 2 is equal to, we're going to use the rectangle, right? So it'll be base, length times width, right? So 2 plus 1, or 2 times 3. It looks almost the same, but that's just coincidence. Let's look at B. B is 2 times 1 plus 2 plus 3 plus 4. But if you look at it in terms of rectangular terms, it's actually 4 times 4 plus the extra 1 on the red, right? I'm looking at B. Look at B. It has 4 in the length and a 5 on the width, or 4 plus 1 on the width. I notate them with colors. Lift up slightly. I like that. Oops. That making sense? How are we doing so far? So, part C then, I didn't draw it, but it was 2 times 1 plus 2 plus 3 plus 4 plus 5. So if you change it into, because this is 2 triangles, right? So it would then be, the triangle's base is 5. And then over here you'll get 5 plus 1. Okay? So, if you want to find them individually, 1 plus 2 will then be 2 times 2 plus 1 over 2, right? And then similarly, 1 plus 2 plus 3 plus 4 will then be 4 times 4 plus 1 over 2. Similarly, 1 plus 2 plus 3 plus 4 plus 5 will then be 5 plus 1 over 2. So, what do you think 1 plus 2 plus 3 plus 4 plus all the way to 100 will equal to? What should that be? (50-50), and it can be given by what equations is. So if you make a triangle, right, 1 to 100, it will start with 100, and then you get 100 plus 1 on the width, on the length, and then you divide it by 2, which is 50-50. How can you use dots to explain? Basically, you do the same thing, right? 1, 2, all the way to 100. Okay, and then you put 100 over on this side too, right? So in reality, this side is actually 101, right? 101. And then because they make a square, I mean not square, a rectangle, you just want this part, right? So it's 100 times 101, and then you divide it by 2 because you only want the triangle part. Does this part convince you? If not, I have an alternative way to look at this. Okay, algebraic way to look at it. This is very famous from the famous mathematician. Name is Gauss. Gauss, I think he is considered a father figure for most mathematician. Father figure, maybe a demigod figure. His name is Gauss. He has like a lot of discovery in math. When he was 5 or something, his math teacher, well, because Gauss too smart, right? You know, like some of you, Gauss too smart. So he's like, this is boring. I can't do math with these kindergartners, right? I'm better than that. So his 5-year-old Gauss was like messing around. And his teacher probably like just want to embarrass him or like put him in his place or whatever. And he's like, hey Gauss, why don't you, if you're so smart, why don't you add from 1 to 100? Okay, when you're done, come talk to me. And he was like, I'm done in like 5 seconds. And the answer is 50-50. And then he was like, and his teacher was like, what? How do you do that? You cheated. And there was no calculator back then, right? You know, this is in the mid-ages. Not mid-ages, but like Gauss age is like Renaissance age? I don't know. I don't know history. I used to know history. But anyway, so the way Gauss did it was the following. Okay, it's very similar to this, but he did this. So he wanted me to add from 1 to 100. Okay, that's what I want to do. But let's switch it around. So there's a 99 here, right? So plus 98 plus all the way to 2 plus 1. What do you notice about these numbers? If you add them up. Well, don't I get a bunch of 101s? How many 101s are there? There are 100, right? So I know together they are 10100. But I only want 2 of them. I mean, I only want 1 of them, right? Because then I divide by 2, I get 50-50. This is the story of Gauss. And Gauss's legacy, the legend. No, there are 100 of them. See? 1, 2, 3, and you count 100 of them, right? But you only want to count, because you added them, right? So you have 2 sets, but you only want 1 set, right? Because the task was 1 to 100, adding up, right? But then he also added 100 to 1, and then they add the 2 lines together, so you get double the amount. Right? So when you add them up, you get 100 of those, and then because you only want 1 set, you divide by 2. Okay? Does that make sense? All right, that's okay. Then let's look at the next page. So what about if I want 1 all the way to n? Well, from our experience, you can just replace any number like that. And this is basically the same triangular method, okay? Method with side n plus 1. Okay? How are we doing? How are we doing? Good? Now, let me show you something else. So, when I have triangular numbers in consecutive, so if you start with 1, so it goes like this, right? Start with 1, right? And then 1 plus 2, right? And then 1 plus 2 plus 3, and then 1 plus 2 plus 3 plus 4, and so on and so forth. These are called, right? This is 3, 6, 10. Remember these numbers? Didn't we do this in one of the general sequences? This is one of the patterns we love, right? Or love is an overstatement, yes. But it's one of the things that we do, right? So if you look at this, how did they come about? How can I find them in geometric sense? So if you look at this, every square, these are called square, okay? Why? Because 3 times 3, 2 times 2, 4 times 4, right? So we're going to circle each one of them. So 1 and 3, then you get what? 3 and 6, right? Triangular. And then 6 and 10, right? And the next one will be 10 and which one's next? 10, 6, 10, 10, 15, and then the next one is 15 and 21. Okay, so these are all triangular numbers. Why do they appear in a square? Because the other part makes up for the next layer, right? Make sense? How are we doing? Now let's take a look at how we can make sense of these. For example, 2 square is made up of first 2 triangular numbers. The T stands for the number of terms of each triangular number, okay? Each triangular number. So 2 square is term 1, term 2, so triangular 1, triangular 2. Why? Because it's 1 plus 3, right? 3 square is 9, which is equivalent to 2 plus 3 on the term number. So you can put T2 plus T3. And then obviously 4 square would be T, 3 T4, right? And then 6 square would be, what would be the pattern? It's not going to be 4 and 5, okay? Because this is 4 to 6, right? What is the pattern here? What do you see? What is the pattern? How do I match the numbers? What should this answer be? Type it in the comments. Five and 6. T5 and T6. Very nice, right? And this will be T14, T15, right? And the last one is Tn minus 1 and Tn, okay? It's just the pattern of indices, right? It's not necessarily a big deal, basically, okay? For the n-term question, would it work for 0? You mean like 0, 0 plus 1 over 2? By definition, I think it will, right? Because if you have 0 sides, then you get what? 0 times 0 plus 1 over 2, right? Isn't that, by definition, 0? Right? So you will have a 0 term. 0 term start with 0, right? No sides at all. Okay? But it won't work with negative numbers. Because that wouldn't make sense, right? Does this make sense? Can I get a comfort level from 1 to 10? Yeah, like you said, Kevin, this is very similar to, well, there is negative possibilities, but it means different. Okay? We'll get to that on the next part when we talk about geometric and arithmetic series. And talk about what they mean when you have a negative number. Okay? All right, so take a look at this. So I want to give you some time to look at this first. Okay, 9 and 10 are pretty good. 7 are pretty good too. Okay. So in the Supreme Court, there are 9 judges. Like, as you know, right? You guys are all expert in government, right? This is true. There are 9 judges. It is customary for all judges to shake each other's hands when they enter a room together. I guess. That I don't know. How many handshakes occur in the room with 9 people? Assume that, everyone actually shake everyone's hand, because probably not anymore right now because, social distancing. Social distancing. Yeah, I know. And there are old people too. Death rate is way high. Okay, sorry. Shouldn't laugh at that. It's very serious. Anyhow, so assume that they could still shake their hands. How many handshakes occur in the room with 9 people? You want to show multiple representation to provide evidence of your answer. This includes a table, diagram for different amount of people, starting with 2, since one person can shake his own hand. I mean, we are defined handshakes between 2 people, okay? I know you probably shake your own hands all the time at home, but we are assuming that you're shaking with another person, okay? All right, so let's represent it. So if you have 2 people, right? So there are multiple representation of this. Okay, let's just start with this. So if you do this, right? So, yeah, it is a similar problem. Oh, sorry. You start with 1 person. Obviously, if you have 1 person, then you get 0 handshakes, right? 2 people, how many handshakes? 1, right? So can you complete, I'll do one more, okay? If you have 3 people, you get 3 handshakes, right? So can you finish with this diagram while I take attendance? If you're here, say you're here, okay? Let's make sure that I can, I got a 36 answer. One seeing Jessica? She here? Okay. Well, Jessica, if you're here later, or if you're here, send me an email, okay? All right, so let us take a look. So the next part is then, so you count, right? After you count, so you keep going. So if you do 4, then you have 4 people. Everybody has to be connected to everybody, okay? So you got 1, 2, 3, 4, and then you cross like this. Check if each one is connected to each one, okay? So that's 1, 2, 3, 4, 5, 6. All right, and you keep going. Once you count them all, you realize it's the same pattern: 1 plus 3 plus 6 plus 10 plus 15 plus all the way. Okay, so that's one of the ways to think about it. Oh, hi, Jessica. Okay, and then okay. So that's one of the ways to represent it. The other way to represent it would be, we're gonna start with the first person's choice, okay? So we're gonna take turns, basically. So the person 1, okay? First person, how many choices? So we're creating new handshakes, okay? New handshakes. Okay, this is a very interesting problem because there's so many ways to think about it, and the more ways you think about it, the more you realize that fundamentally they're all different type of thinking, but they end up with the same answer. Okay, so person 1, if you think about it, how many new handshake can you create being the first person that initiates the handshakes? So no one else gets to handshake anybody except for you. Okay, so how many new handshakes can you create being the person 1? Think about it like that. How many new handshakes can you create? Type in the chat. 8, right? 8 makes sense, right? Because there's 9 people, you're one of them. You can create 8 new handshakes, right? Now you're done. All right, the next person come in. Notice that this person already shaken his hand with you, right? So how many new handshakes can he create? Well, other than you, he can create any. So I'm gonna line this up real quick. P3, P4, P5, right? P6, P7, P8, P9, right? Like this. So then the next person can only shake 7 people, right? Everybody after him, right? He can create new handshakes with. Similarly, P3 can only shake everybody after him, and then P4, P5, P6, P7, P1, and obviously when it's P9's turn, you realize, oh, wait, no, I don't get to initiate because everything has been done. Okay? So that's the idea. So you're adding from 0 to 8, or 1 to 8, in a sense. So if you add it up, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, then you go back to the same problem of, so you can line it up, right? 1 to 8, that will be 8 times 1 plus 8 over 2, which is 36. Okay, this is a very interesting part. Okay, I want to look at this part real quick so that we can talk about how exactly did you come up with this kind of sum. Okay, so usually when I think about sum, you know, we can use the triangle method, right? We did the triangle before, right? Like that. But that reminds me of something else. So can't we do similar things with things like a trapezoid? You remember trapezoidal formula? If you have base 1, base 2, right? And you reflect it, it will be base 1, base 2 as well. And there's a height here. So when you do your trapezoid formula, don't you do like 1/2 base 1 plus base 2 times height to get the area? Okay. So if that makes sense, then I can do 1/2 first term, in this case, is 0, plus last term, which is 8. Since they're going down linearly, right, they're all off by 1, times number of people, which is in this case 9, and divided by 2. So it will be 1/2 0 plus 8 times 9 divided by 2, which is 36. Or you can treat this as, okay, I'm not counting the 9th person, so I'm just counting 1 to 8. If that's the case, then your equation could be changed to the one we had, which is 1 plus 8, but there's only 8 people I'm counting, divided by 2. That will also give you 36, regardless of how you think about it. Okay? So that is slightly more algebraic thinking, but from a geometric trapezoidal standpoint. Kind of makes sense? So finally, because that's the case, in your equation, if you want to find n people, let's just say, let's do one more, okay? We have like 30 people in our class, right? When we have 30 people in class, say we can shake people, how many handshakes can I create from the class? Well, the other way to think about it is A, how many handshakes per person can I get? 9 total, right? But you have 30 people. I know. You have 30 people. But if you handshake with me, I handshake with you, so you got to divide it by 2. Right? This is the same structure as what? N minus 1 times n over 2. Right? Or you can think about this as a trapezoid one, which is the first person will shake 30 times. Wait, or shake 29 times. Last person won't shake at all, and there's 30 of you. Right? You can think about it like this as well. And divide by 2. Okay? Alright. So, finally, that's your equation for n. Right? N people. Comfort level 1 to 10 after seeing this problem. Could be higher, could be lower. Solid 10. 8.5. 8. Okay. Seems pretty good. So before you go, let me give you your homework. So your homework is again on Google Classroom, obviously. Please do your homework, okay? If you don't do your homework, then you're asking for trouble, okay? You're in danger yourself of not getting credit, which is like the easiest thing to do to get credit for this class, right? So, do your homework, come to class, end the story, okay? There's no formative assessment this week. So just Google Classroom, there should be a worksheet called Square Numbers. Okay, Square Numbers. This is due on Sunday night, May 3rd. Okay, there's only one worksheet, I think. So just finish that one and turn it in time. Okay. Any other concerns and questions before I play the music and let you go? No, so cheetah. Now you say you're here? Right. The negative version of Tn is basically the same idea as arithmetic sequence with difference negative, or arithmetic series of distance negative. So when you add, the more negative it gets, the more negative. So like you can think of them as a positive, but when you add, it's negative numbers. Like -1 plus -2, right? -1 plus -2 plus -3, -1 plus -2 plus 3, -3 plus -4. Right, so it's like in reverse. Think about it like this. Like you had your positive ones, right? Like 1, 2, 3, right? 4. So it's the exact same thing, but because you're doing negatives, you have negative numbers instead. But the way the number turns out will be the same, except it's on the other side. And you can't really, I mean, it's the same calculation. That makes sense. When you multiply both negatives. So the number of terms, like the calculation, the equation will change as well, because it's not going to be the same. It's going to be negative, right? All your sums will be negative. So when you're doing your formula, you have to fundamentally change it, because like for example, okay, these will get canceled out basically. So you just plug in as it is. So for example, if you start from here to here, right? From here to here, then you'll get -3 plus 4. This is 4, right? 4 times number of terms. So 1, 2, 3, 4, 5, 6, 7. That's the difference in number 7 divided by 2. Okay, that way you'll get wait, 3, 4 divided by 2. Does that even make sense? What am I calculating? 1, 2, 3, 4, 5, 6, 7, 8. 7 doesn't sound right. What do I do? 3, 2, 1. Oh, there's a 0 in between. There's a 0 in between. So it's actually 8 terms. So divided by 2, so you get 4 times, so it would be positive 4. Which means that these will cancel, and you just get this part. Okay? 0 is a term as well, right? T0. Right? There's nothing here. So it's the same exact way you calculate it, but you can't just strictly use n-1 because n-1 has a sense of like the index number terms. So like when you plug in, say like both negative numbers, then you'll get a positive. But in reality, the sum is negative, right? For example, if you go from here to here, right? But the sum with the trapezoidal work is still applied. Okay. Hope that answers your question, kind of. Alright, if nothing else then, no problem. I'll just play another music and say goodbye. Have a good week. Do your homework. Thanks, bye. It's called Technoledge by Peter Spacey.